just 5 minutes of charging. That single number alone was enough to electrify the audience at CES 2026. On stage, Donut Lab presented what sounded like the holy grail of the electric vehicle industry, a solid-state battery that could be fully charged in 5 minutes. The crowd was invited to imagine a future where charging is faster than buying a cup of coffee. But here is the uncomfortable truth. 5 minutes charging is not a miracle that breaks the laws of physics, and the reality behind this battery technology may leave you deeply disappointed. What is the problem with Donut Lab's solid-state battery technology? Let's deep dive into this episode today. To charge any battery in 5 minutes requires an extreme electrical condition. In engineering terms, it demands a charging rate of roughly 12 C. This means the charging current must be 12 times the battery's rated capacity. By comparison, most consumer lithium-ion batteries are charged at about 0.5 C to 1 C, which corresponds to 1 to 2 hours for a full charge. Moreover, even high-performance electric vehicles rarely exceed 3 C, and only for a brief window at low state of charge. Consider today's fastest public charging systems. Tesla V3 and V4 superchargers peak at around 250 kilowatts. At first glance, that sounds enormous. However, on a 75 kilowatt-hour battery, that peak corresponds to roughly 3 C, and it quickly tapers down. As a result, the full charging session still takes 20 to 30 minutes. This taper exists for one reason, and that reason is heat. Now, apply Donut Lab's 5-minute claim to a realistic vehicle. A 100 kilowatt-hour battery charged in 5 minutes requires a sustained power delivery of approximately 1.2 megawatts. This is not a rounding error. In fact, 1.2 megawatts equals 1,200 kilowatts. Moreover, it is nearly 5 times higher than Tesla's fastest chargers and roughly equivalent to the peak load of a small industrial facility. Even more critically, many highway substations are not designed to deliver that level of power to a single outlet. This is where expectations quietly break. 5-minute charging is not only a battery challenge, it is, in addition, a grid challenge. A charging plaza with 10 vehicles charging simultaneously at 1.2 megawatts would demand 12 megawatts of capacity. For reference, a typical urban neighborhood often peaks at just 2 to 5 megawatts. Consequently, scaling this infrastructure nationwide would require massive upgrades in transformers, cabling, and grid stability systems. The second layer of reality is thermal physics. Electrical heating inside a battery follows Joule's law, where heat scales with the square of the current. Therefore, increasing charging current from 3 C to 12 C does not produce 4 times more heat. Instead, it produces roughly 16 times more heat. This is precisely why lithium-ion batteries aggressively limit charge rates. At internal temperatures above 60 degrees Celsius, degradation accelerates rapidly. At around 100 degrees, conventional lithium-ion cells risk thermal runaway. Donut Lab's core claim, however, is that its solid-state chemistry operates in a fundamentally different regime. The company states that its cells retain 99% capacity even when operating at 100 degrees Celsius. In contrast, standard lithium-ion cells often lose measurable capacity after only minutes above 80 degrees. This difference matters. Higher temperature increases ion mobility, which, in turn, supports faster charge and discharge. In addition, the mechanism Donut Lab describes relies heavily on pseudo-capacitance. Instead of lithium ions diffusing deep into electrode structures over micrometer distances, ions interact primarily at the surface. As a result, diffusion time and internal resistance are reduced. In laboratory terms, this can dramatically increase power density. Supercapacitors already demonstrate charge times measured in seconds. However, they do so by sacrificing energy density. Donut Lab positions its technology between a battery and a capacitor, trading some energy density for extreme power capability. Once again, numbers tell the story. Typical lithium-ion batteries achieve energy densities of 250 to 300 watt-hours per kilogram. Public information suggests Donut Lab's early solid-state systems operate at lower energy density, closer to 100 to 150 watt-hours per kilogram. This is still usable, especially for smaller vehicles. Nevertheless, it means more mass is required to store the same amount of energy. Now compare that with a full-size electric SUV using a 100 kilowatt-hour pack. The required power jumps 5-fold. Consequently, thermal gradients across the pack increase, mechanical stresses between cells intensify, and system complexity grows. Moreover, even minor inconsistencies in manufacturing tolerance can lead to uneven heating, which accelerates degradation in localized regions. Over hundreds or thousands of cycles, these small differences matter far more than headline charging speed. History strongly supports this caution. Over the last decade, dozens of battery startups have demonstrated remarkable laboratory results, only to struggle with mass production. Cycle life often drops sharply when cells are charged aggressively. A battery that survives 500 cycles at 12C may sound impressive. However, when compared with modern electric vehicles designed for 2,000 to 3,000 cycles at 1C, the gap becomes obvious. For a 100 kilowatt-hour vehicle, that difference can translate into 300,000 kilometers versus less than 100,000. For this reason, 5-minute charging should not be viewed as a replacement for existing lithium-ion systems. Instead, it is better understood as a specialized solution. Applications where downtime is extremely expensive, such as delivery fleets, industrial robotics, or electric motorcycles, may benefit enormously. In those contexts, building dedicated high-power charging infrastructure actually makes economic sense. The problem arises, however, when the public narrative jumps from specialized use to universal adoption. 5 minutes sounds like gasoline refueling. Yet gasoline stations rely on energy that was refined, transported, and stored elsewhere. Electric charging, by contrast, concentrates energy delivery at the point of use. Physics simply does not allow that concentration without consequences. The real truth about Donut Labs' solid-state battery is not that it fails. Rather, it exposes the limits of our expectations. 5-minute charging is possible, but it is expensive, infrastructure-heavy, and optimized for specific scales. It is not a magic eraser for range anxiety. Instead, it is a sharp tool that works best when applied carefully. Ultimately, when the numbers are placed side by side, the excitement becomes grounded. And in that grounding, the technology becomes more credible, not less. Because progress in energy has never come from miracles, but from understanding exactly what the numbers demand and deciding where those demands are truly worth paying. What do you think of this supposedly groundbreaking technology? Could it completely replace lithium batteries? Give your ideas in the comments below. Thank you, fellas.